Today we're going to look at numbers written as powers, and we're going to go through some calculations involving them. And in particular we're going to look at square roots and the square roots of numbers which give us an irrational answer. That is, numbers which can't be written as whole numbers or fractions. Now these types of square roots are called surds, but more of that later. What I want to do first is a little bit of revision, and we'll start with something that we know. 2 cubed is written as 2 multiplied by 2 multiplied by 2. It's a neat way of writing this repeated multiplication. And we say that 3 is the power or index, and 2 is raised to that power or index. And the value of 2 cubed works out to be 8, because it's 2 times 2 times 2. So, if we had 4 cubed, that is 4 times 4 times 4, and we know when that's worked out is 64. But what if we have 4 to the negative 3? What would be its value, and how could we put it down more neatly? Well, we go back to what we know. 4 cubed equals 4 times 4 times 4, which is 64. 4 squared equals 4 times 4, and that equals 16. 4 to the power 1 is 4, and 4 to the 0, well, if we look at our pattern in our calculations, we are dividing by 4 each time, and the index, our power, decreases by 1. So 4 to the 0 must be 4 divided by 4, which equals 1. But we're interested in finding out about 4 to the negative 3. So we'll continue our pattern of multiplications. 4 to the negative 1 will be the 1 divided by 4, which is a quarter. And 4 to the negative 2 must be a quarter divided by 4, which is 16. And 4 to the negative 3 must be 1/16 divided by 4, which is 1 over 64. But if we go back to this line, we know that 4 cubed is 64. So we can rewrite 1 over 64 as 1 over 4 cubed. And look at that. 4 to the negative 3 is 1 over 4 cubed. So 4 to the negative 2 is 1 over 16, must be 1 over 4 squared. And 4 to the negative 1 must equal 1 over 4 to the power 1, which is 1 over 4. So negative powers give you the reciprocal of the number. That is 1 over the number. So if I had this example, 3 to the negative 2, we can write that as 1 over 3 squared. And 1 over 3 squared is the same as 1 over 9. What about this one? 5 to the negative 3. How can we rewrite that, and what's its value? Well, the negative 3 means it's 1 over 5 cubed. And that is 1 over 5 cubed is 125. So 5 to the negative 3 is 1 over 125. Now, the big thing to note is that even though you've got a negative power, the value that you get is a positive answer. That's a big mistake by quite a lot of people. They think when you've got a negative power, you'll get a negative answer. So please don't make that mistake. A negative power means reciprocal of the number, 1 over the power. Moving on. In the examples that I've just been doing, we've used positive and negative integers for the powers. But what if we have fractional indices or fractional powers? How can we represent them? What's their value? Well, again, we'll start with what we know. We know that 4 to the power 1 is 4. But what would be 4 to the half? What's its value? Well, looking at this, we know, using indices laws, that 4 to the half times by 4 to the half must equal 4 to the indices added together. And a half plus a half is 1. But 4 to the 1 is just 4. So 4 to the half times 4 to the half equals 4. That means that it's something times by itself equals 4. Well, we know that. It's obvious. It's 2. 2 times 2 equals 4. So 4 to the half equals 2. So 4 to the half is equal to 2. And we write this in a shorthand notation by doing this. 4 to the half is equal to the square root of 4. And that is the symbol for the square root. So the half is associated with the square rooting of a number. So if we had 9 to the power of a half, that's the same as the square root of 9, which equals 3. So in general, if we had a number a raised to the power a half, then we can write that as the square root of a. We can continue this on by saying if we wanted the cube root of a number, say 4 to the third, we can write that as the cube root of 4, like this. And the fraction associated with the cube root is a third. Similarly, the fourth root. So if we had 5, the fourth root of 5, you can write that using this shorthand notation with the small 4 there and then this root symbol. And the quarter is associated with the fourth root. So if we had the nth root of a number a, we can write it like this in shorthand. So if we have the cube root of 64, we can write it like this, and it equals 64 raised to the power of a third. Now we know 64 is 4 times 4 times 4, and that's raised to the power of a third. And the answer is dead easy. We want to know what number times by itself 3 times gives you 64. Well, it's obvious because of what we've just written. It must be 4. So the cube root of 64 is 4. A very useful, simple fact leading on from this that is known but people tend to forget it is that we know that 4 to the half times by 4 to the half equals 4. That is, the square root of 4 times by the square root of 4 is 4. And we can write that more simply by saying it's the square root of 4 squared equals 4. Now, I'll be using this very simple fact later on at the end of the session, so remember it. It's any number, the square root of it, squared gives you that number. Another important thing to remember about surds comes from solving this equation. If we had this very simple quadratic equation, x squared equal 4. If we take the square root of 4, we know that we have to have 2 roots for the solution because this is a quadratic equation. So x equals plus or minus the square root of 4. So we know that is positive 2 or negative 2. You've got two roots. So roots are not unique. And remember, we don't always have to write the positive sign. We can write positive 2 as 2. And remember, if you haven't got a sign in front of the square root, then it's assumed it's a positive square root. When it's not, you have to put the sign in and make it a negative square root. But the positive square roots are the ones that are most common. Now moving on, what I'd like to do is actually do some work on the square root of negative numbers. We've done the square root of positive numbers. What if we had the square root of negative 9? Can we evaluate this? Well, the square root of negative 9 can be written as negative 9 raised to the power of a half. And so what we're looking for are two numbers multiplied by themselves, which will give us negative 9. Well, we know 3 times 3 is 9, and negative 3 times negative 3 is 9. But there's not two numbers multiplied by themselves, which will give us negative 9. So you cannot evaluate the square root of a negative number and get a real answer. Now what I'd like to do is continue on using surds in some calculations and go over some common square roots that you might know. Now we all know that the square root of 25 is 5, because 5 times 5 is 25. And if we were given the square root of 9 over 4, that's dead easy. It must be 3 over 2, because 3 times 3 is 9, 2 times 2 is 4, and we write that as 1.5. But we've now taken square roots of whole numbers and fractions, and we've got answers that are whole numbers and fractions. But there are other square roots in which we don't get whole numbers or fractions. We get them as non-terminating decimals, such as root 2. Root 2 cannot be evaluated as a whole number or a fraction. Neither can root 3. We can only write them as approximations. They are irrational numbers. An approximation for the square root of 2 to 3 decimal places is 1.414. Approximation for root 3 to 3 decimal places, and I'll put 3 decimal places just to remind us, is 1.732. Now, because they cannot be evaluated as whole numbers and fractions, and these are irrational numbers, they're very special, and we call them surds. Other common surds would be root 5, root 6, root 7, root 8, not root 9 because we know that's 3, and root 10. Now, why do we need to know about surds? Well, surds crop up a lot when we're using Pythagoras' theorem and in trigonometry. And so we need to know how to manipulate these in various calculations. And we need to know how to simplify them as well. Now, root 2 cannot be simplified any further. Neither can root 3 or root 5, root 6, root 7. But look at root 8. If we take the square root of 8, 8 can be replaced by the product 4 times 2. Now, the square root of a product is the product of the square roots. So it's square root of 4 times by the square root of 2. We know the square root of 4 is 2, and this is root 2. So the square root of 8 can be written more simply as 2 square root of 2, or 2 root 2 in shorthand. What about this one? What about the square root of 5 times by the square root of 15? Now, in the previous example, the product of the square roots is equal to the square root of the products. So we use that fact to rewrite this expression in another way. The square root of 5 times by the square root of 15 is the square root of 5 times by 15. And that is the square root of 75. But 75 can be rewritten as 25 times by 3. Note 25 is a square number. And we can then separate that out to say that is the square root of 25 times by the square root of 3. Square root of 25 is 5 times by root 3. So the square root of 5 times the square root of 15 is 5 root 3. What could be easier? But a common mistake is that people would take an expression like this, a surd in the form of the square root of 4 plus 9, and say it's equal to the square root of 4 plus the square root of 9. Now this can't happen, because if we follow this through, that would be 2 plus 3, which would equal 5. This is not correct, because 5 is the square root of 25. And here we've got 4 plus 9, which is 13. So the square root of an addition is not equal to the square root plus the other square root. So please remember that. Those two rules that we previously did with surds and the expansion of multiplications only applies to multiplication and division, not to addition and subtraction. So if we move on and we take the square root of bigger numbers times by the square root of another big number, the square root of 400 times by the square root of 90, it's useful to remember the square numbers, the typical square numbers, the square numbers of the numbers 1 to 10. That's 1, 4, 9, 16, 25, 49, 64, 81 and 100. You should be able to remember those straight off and recall them. And this helps us to rewrite these square roots. We can write square root of 400 as the square root of 4 times by 100, and the square root of 90 is the square root of 9 times 10. Then we expand out and we say that this product and the square root of that product is the square root of 4 times by the square root of 100 times by the square root of 9 times by the square root of 10. Then we simplify. We know the square root of 4 because it's a square number, it's 2. We know the square root of 100 is 10. Square root of 9 is 3. But the square root of 10 is just the square root of 10. And we neaten it up by multiplying these three numbers together. That's 2 times 10 times 3 is 60. 60 root 10. Delicious. What if we had a quotient involving square roots? What if we had the square root of 2000 divided by the square root of 50? Well, we use a similar rule to the way that we use the rule for multiplication. We can say that that is equal to the square root of 2000 divided by 50. We cancel down and we get that the answer is the square root of 40. But we can simplify the square root of 40, thinking of square numbers, break down 40 as 4 times 10, And that equals the square root of 4 times the square root of 10, which is 2 times the square root of 10. What could be simpler? It becomes second nature, really. The more practice you do with the rules, the more you understand them and you don't have to think about them. Now, these simplifications of surds are quite easy ones. But what if we had this expression involving surds? It's a little bit different from the expressions that we've already used. 1 plus square root of 3 times by 2 minus the square root of 2. How do we expand out an expression like this? Well, we do it just in the same way as we did normally. We use the first number in these brackets and multiply it by these two numbers, and then we use this number and multiply it by these two numbers and combine them together if possible. So if we do that, we multiply 1 by these two numbers and we get 2 minus the square root of 2. Then we multiply by square root of 3. That is, square root of 3 times 2 is 2 square root of 3. And then the square root of 3 times negative square root of 2, which is your subtract root 3 root 2. Now, when we look at that expression and consider it, you can see that we can't really simplify it any further. But what if we had this expression, similar to the one above, using two brackets, but look at the numbers and the surds involved. 1 plus square root of 3 times by 1 minus the square root of 3. The number's the same, but the operation's different. See what happens when we multiply out in the usual way. 1 times 1 minus root 3 is 1 minus root 3. Then root 3 times these two. Root 3 times 1 is plus root 3. Root 3 times by minus root 3 is subtract root 3 root 3. Now remember that little fact that we did previously. This is root 3 squared. And what's root 3 squared? It's just 3. So we can look at our expression and we can see that that is 1. And lo and behold, look what happens here in the middle. Subtract root 3, add root 3, they cancel. And so we're left with 1 minus this, which is 3. 1 minus 3 is negative 2. So we started off with a multiplication of brackets which involve surds, but look what happens with the answer. We've got a whole number with no surds involved. Now this is a significant fact, and in fact this is so well known it's given a name. This type of expansion is given a name. It's called the difference of two squares. And the difference of two squares is written as a squared minus b squared, and it can be expanded by using two brackets into a minus b times by a plus b. Now can you see that this is similar to what we had up here, where a is 1 and b is root 3. So our product here, 1 plus root 3 times by 1 minus root 3, is really the difference of two squares, and the two squares are 1 squared minus root 3 squared. Again, notice we're using that simple fact which makes things really easy. That is 1 minus 3, which is negative 2. So if you remember this expansion, the difference of two squares, this is very helpful sometimes when you have calculations involving surds. Now, sometimes you have surds written like this, 1 over the square root of 13. Now, really, we don't like answers being given such that the denominator is a surd. What we want to do is give an answer with a whole number as the denominator. Now, there's a technique that helps us to change this surd into a whole number, and that technique is called rationalization. What we have to do is rationalize the root 13. We have to make it into a whole number. Now, the easy way to do that is to use that simple fact that keeps cropping up time and time again, is that we have to multiply it by itself. But we don't want to change the value of this fraction. So what we have to do is multiply it by the fraction square root of 13 over the square root of 13, because that fraction is equal to 1. Now, when we do that and evaluate it, the square root of 13 times the square root of 13 is 13. And on top, 1 times the square root of 13 is the square root of 13. And this is the more acceptable form of writing 1 over the square root of 13. It's where you have, as I said before, a whole number as the denominator. Now we can get more complicated fractions which involve surds. What if we had this fraction, 1 over 1 plus the square root of 2? How can we rationalize that? How can we make this addition into a whole number? Well, remember what we've just done on the previous examples. We used the difference of two squares. And the difference of two squares had an expansion where you had the two numbers the same, but the operation was different. So what if we multiplied the 1 plus the square root of 2 by 1 minus root 2? Now, what we've got on the bottom is the expansion of the difference of two squares, and we know that will give us a whole number. But we want to leave that this fraction has the same value, so we have to multiply it by the fraction 1 minus root 2 over 1 minus root 2, because that fraction equals 1. So we evaluate what we've got. Now remember, this was the expansion of two squares. And what are the two squares? It's 1 squared and the square root of 2. 1 squared minus the square root of 2. That's what this product is. When we evaluate that, that equals 1 minus 2, which equals negative 1. Now we simplify all of this. 1 times 1 minus square root of 2 is 1 minus the square root of 2, all over negative 1. Now that doesn't look really neat. What we will do now is neaten it up. We divide through by the negative 1. And we divide through by the negative 1, we get negative 1 into 1, which is negative 1. Then negative 1 into the negative root 2 will give us plus root 2. And we'll just rewrite it so that we've got the positive number first. Root 2 subtract 1. So when we rationalize this fraction, 1 over 1 plus the square root of 2, you get the square root of 2 minus 1. Isn't that really neat? It looks great. You've got a fraction here, but here you've just got a subtraction. One final example, a little bit more difficult than the previous ones. See how we can cope with this. 1 over the square root of 5 minus the square root of 3. We want to rationalize this fraction. Think of the difference of two squares. We've got root 5 minus root 3. If we multiply it by root 5 plus root 3, we know that that expansion is the difference of two squares. We don't want to change the value of the original fraction, so we have to multiply it by another fraction, which equals 1, and that will be square root of 5 plus 3 over the square root of 5 plus the square root of 3. We work out this expansion using the difference of two squares. The two squares involved are the square root of 5 subtract the square root of 3. When we evaluate that, that is 5 minus 3, which equals 2. So when we rewrite all of this, 1 times the square root of 5 plus the square root of 3 on top over 2. We tidy it up a little bit by dividing through by the 2, and so we get the square root of 5 over 2 plus the square root of 3 over 2. So that's it. That's how you rationalize surds. You have to make the surd denominator into a whole number by multiplying the fraction by another fraction, which is 1. And it's helpful to remember the difference of two squares. Now what I want to do is finish off by giving you my top tips on surds. First of all, recap what is a surd. A surd is a fractional root of a whole number, like a square root or a cube root, that gives you an irrational number. Now remember, an irrational number is a number that cannot be written as a whole number or a fraction. And remember, there are common surds that we use a lot. That's root 2, root 3, root 5, and so on. And there's certain basic rules that we know that are useful when we are doing calculations involving surds. One of them is, if you have the square root of a product, then that can equal the square root of one number times by the square root of the other number. And similarly, the square root of a quotient is the square root of one number divided by the other square root. But remember, the square root of addition is not the sum of the square roots. That's a common mistake, so don't make it. Another technique that we use in surd calculations is rationalization. We don't like surds being the denominators of fractions. So what we have to do is rationalize the fraction. We multiply by a fraction that's equal to 1, and sometimes when we have to do that, the difference of two squares is useful. The expansion of the difference of two squares is a squared minus b squared is a minus b times a plus b. Now if you know all of those top tips, I think you'll be pretty good in doing calculations involving surds.